essentially how we anticipated this. But if you were a mentor, if you're coming here to judge, if you're coming to give feedback, I really appreciate the involvement that you have with our students. All of the industry involvement just makes our program stronger and is a really great experience for our students. So thank you for your time and efforts. I appreciate it. So, and then I'm going to say goodbye to all of you. Good luck with all of it. I'm sure that it's going to go famously. I would love to be able to stay, but I have grading to do and a Geotech 1 exam to work on, and most of you probably remember that. So with that in mind, good luck to everyone. I hope everyone's staying safe and healthy. Thank you, Dr. Nguyen, for doing this, and have a good one.
Thank you, Dr. K. Oh, by the way, Julio, can you stop sharing your Julio?
Yeah, I'm trying to do that. Supposed to be sharing. I'm not too well versed in this thing.
Oh, okay, no problem. I will stop. It already stopped.
It should be there.
Pardon?
You cannot see me. You cannot see me.
Yes, but let me start with. Okay, the first thing, can you share your screen now? Just to override. Can you share your screen? Just to
it won't let us share the screen. It says you cannot start screen share while the other participant is sharing.
So you just override, is that okay? Yes, you just say yes.
It won't. That's not an option. It just says you cannot start screen sharing while the other participant is sharing.
Okay, so let me start.
Okay.
Let me start that when Julio.
Okay, I see the whole screen now.
Oh, you already see that?
Yeah, I see a whole screen for.
Okay.
Okay, I can see you.
Perfect.
Dr.
Now.
Long. Yeah.
Oh, okay. So now you can share, right, Spencer?
Yep.
Okay, perfect. So good afternoon, everyone. Thank you for the church and for students to join today. And of course, thank you for the mentor that spent with us for the whole semester. And like Dr. K, it's unexpected, but hopefully we'll get through it in this 2 minutes. 2 hours. Very good. And for the logistics, we had 15 minutes for each team in total. So each team will present 10 to 12 minutes, and you will have Q&A in 5 to 3 minutes, depends on how long the team present, 10 or 12 minutes. And I will send a private message to the team when it's 10 minutes. And I will say timeout for EBIT 15 minutes so that we can keep everyone within 2 hours. So with that, let me turn the floor to the first team, which is AEY Engineering, and the mentor are Mr. Hurst and Nathan Levy.
Alrighty, can everybody see and hear us all right?
Yes.
Okay.
Yes.
I just want to make sure we also have Logan and Marcos on here. Ryan is sitting beside me, but I just want to make sure we have Logan and Marcos before we start.
I'm here. Yeah, I'm here.
Okay, perfect. All right, we'll get started then. So as Dr. N said, our team was AEY Engineering. Our project was phase 5B of the Maple Ridge development at Ave Maria. And as he also said, our mentors were David Hurst and Nathan Levy from Peninsula Engineering. Oh, there we go, sorry.
So phase 5B is an additional 121 residential unit with associated roadway utility and stormwater infrastructure. Phase 5B will tie into existing utility and sanitary sewer connections. If you can see the diagram on the far right, the drainage from the site will discharge into 3 previously permitted lakes to the south and east. Due to the existing permits for the site, the project has a few constraints, which Marcos will elaborate on the next slide.
No están abiertas,
Hello, everyone. Like Michael said, Maple Ridge is a continuation of the master development that surrounds it. That means there will be existing infrastructure like existing lakes that are already permitted with control elevations. There's roadway elevations of which are already constructed. There's also already existing potable water connections or water main connections, meaning we will have to use same size infrastructure in order to be able to tie into the master development. Lastly, there is existing gravity sewer elevations that we will have to take into consideration. Other constraints are things like code requirements, like setbacks that are required by Collier County land development. Another aspect to be considered is that our client stated that larger lot sizes were selling better than the smaller ones. And lastly, we have our pervious to impervious ratio that will result dependent on like the lot configurations.
So the scope of the design and the objective. Scope of the design is going to be the analysis of the current site conditions and then proposal of different development scenarios and lot configurations, as well as the design of the sanitary sewer and stormwater system. So the objective by designing these would be to ensure that all Collier County development codes and the water management district requirements are met and that the client's expectations are met or exceeded. So here's a map of the master site plan and the existing conditions around. You can see the existing phases in green and phase 5B, which we are designing, highlighted in blue. It must fit into the existing conditions where you can see there's 4 connection points into the previous phases for access to roads, utilities, and storm drainage. And then we'll be using those 3 lakes, as Ryan mentioned, to mitigate runoff.
Marcos, you still there?
Oh, sorry, I forgot to unmute. Apologize. Okay, so our first design option would be to use 55 and 65 foot front width lots only. So as you can see in the bottom right in green, this is a green space we would be utilizing. It's previously planned as parking space, but we would use it for these larger lot sizes. And then as you see it in the red arrows, those are our previously constructed on-site lakes, and we would use those for stormwater retention and treatment. Here's our second design option. This would be to create only 65 foot width lot sizes. This is considered an option because our client did state that the larger lot sizes were selling better, and it also creates uniformity. So in this option, it's different from design option 1 because we would be using all the previously planned park space for the larger lot sizes. And again, underground utilities will hook up to the already existing underground utilities. Here's our third design option, which would be to create only 55 foot front width lots. This would maximize the amount of lots in our development, which would exceed the 121 lots. Also, we would still connect to this existing utilities, but we would also have to consider if we are having more than 121 lots, if it will create any problems with existing infrastructure. Stormwater calculation would be done using the existing ponds again.
So the option selection was, we ended up going with the one with the multiple front width, and we tried to maximize the amount of 55 and 65 foot front width lots. And the contributing factor to that was, as we spoke about earlier, they were selling better, our client mentioned. So we figured that by maximizing that would maximize sales, as well as utilizing the previously constructed lakes would obviously reduce cost in engineering construction because they're already built and permitted.
Okay, so here we have some of the preliminary utility engineering assumptions. For this design, we focused on ensuring a water distribution network that would meet the requirements of the Land Development Code. To model the network, several design assumptions were necessary. WaterCAD was the program used to simulate the network. To model the existing connections, reservoirs were used at the connection points, provided with an existing water pressure of 89 psi that was provided to us. At the connections, the reservoirs were set at a foot of head of 205.59 to resemble a pressure of 89 psi at each of these connection points. Next, junctions were used to connect hydrants to the water main. The hydrants require 2,000 gallons per minute per the Land Development Code and need to be spaced at 400 feet, also per the Land Development Code. Junctions are also used to simulate demands of the 121 residential units. However, for this design, the focus is ensuring that 2,000 gallons per minute is available for each of the hydrants to meet the fire flow requirements.
All right, so some of the preliminary stormwater management engineering assumptions. So as stated before, this is a master plan community, Ave Maria, very large community. So phase 5B actually lies within the basins PS1-N and PS1-S, which are the north and south areas of that basin. So the stormwater runoff is going to be managed by using overland flow off the lots to a series of swales, some valley gutters, and catch basins in order to discharge it into the 3 existing lakes for retention and treatment.
So this is the site plan design. And as you can see, that green space that once existed around the cul-de-sac was used to maximize the lot sizes. Up until you can see on the right side of the cul-de-sac, we decided, it says dog park, it's just a green space. We decided that space could not be utilized for a lot just because of the awkward shape that it was. But all of the existing lots on that road were either extended 10 or 5 feet to make them 55 or 65 feet wide in the front to maximize the sales opportunity.
All right, so for the actual stormwater management design, we employed a Bentley program, StormCAD, which I'm sure many of you are familiar with. This was used to ensure that the existing lakes were ample to handle the discharge and the treatment due to the new construction of phase 5B. I mean, the model produced can be seen right here on the right side of the screen, which is comprised of a series of catch basins and yard drains, various sizes and types of pipes, including concrete and HDPE pipes, and 9 outfalls to the existing retention lakes, 3 of those. And this model was created, Nathan was able to help us a little bit with this. We had some licensing issues, stuff like that. So we want to thank Nathan for helping us with this. So StormCAD utilizes the NRCS curve number method, which I'm sure many of you are familiar with. So I won't take too much time up. I know we're running low on time here to talk about that. But as you can see here, after creating the model, the program was run and the results can be seen here. This was just the outfall table, excuse me. But as you can see, the HCL does not exceed the tailwater elevation at any point, which shows that the existing lakes can be used to treat and store the maximum discharge.
After completing the initial model setup, for the utility design, the project required 15 hydrants per the spacing requirements. As shown in the table, the local fire flow required was set at 2,000 gallons per minute with an upper limit of 5,000 gallons per minute. By examining the existing conditions, the site contained 5 water main connections, each with a pressure of 89 psi. Not shown are the corresponding junctions that exist where hydrants connect to the water main and also where the pipe changes directions. Junctions are able to simulate demand for residential units. However, for this design, they focus on showing available fire flow, neglecting the residential water demand. So pipe sizing is also an important component of this design. For the initial simulation, a pipe size of 6-inch PVC was used over the entire network. After viewing the results as shown, the available fire flow exceeds 4,000 gallons per minute at all 15 hydrants, so we did not increase the pipe size. Therefore, to conclude the utility design, a 6-inch PVC water main can be used over the entire network.
Okay. And I already touched on this presenting slide 15, but so in conclusion, we did conclude that the demand could be met by the 3 existing retention lakes on site for the new construction and runoff due to the new construction.
So we'd just like to thank our mentor, David Hurst, as well as Nathan Levy for helping us out with this. And of course, our instructor and Dr. T for also helping us out with some of the programs.
All right, and that'll wrap up our presentation with just a couple references here that we used. Does anybody have any questions, or do we have time for questions? I saw your message, Dr. N.
How are we going to handle asking a question? Do we going to take turns or just raise up my hand?
Dr. Wen, you're on mute.
Oh, yeah. Just go ahead to ask, Ayub.
All right. When you run the 6-inch water line, did you just run it for the fire flow requirements, or did you count for residential using that water line? And does that 6-inch meet the minimum require Collier County utility guideline?
That's a great question. So when I originally met with Nathan, one of our mentors, to set the model up, we focused on ensuring that fire flow could be met while neglecting residential demand. In a real world setting, I absolutely would have computed the demand for each of the residential units, and I would have applied them at the junctions. But for this model, we used the 6-inch, and because it was over 4,000 gallons per minute, we went ahead and assumed that it would be suitable to meet the demand of the residential units.
Okay, and one more question. When you run your hydraulic calculation for the drainage, did you look at the existing outfall structures? Do you need to change? Do you have to do any modification to the weir elevation?
I'm sorry, you broke up there for a second. Can you repeat that question again?
When you run the hydraulics calcs for your water management, did you look at the existing outfall structures, weir elevation, and they have to be modified?
They were not. They were previously constructed and in place, so we didn't specifically look at their elevations on the weirs. We just wanted to ensure, just for the scope of this project, that they would be ample to handle the flow from the new the new construction. We did not specifically check the outfall structures with the weirs because they were, well, A, already in place, and B, that would be something that would add a little bit of a cost for our client. And so just for the scope of this project specifically, we did not check those weir elevations. No, to answer your question. But obviously in the real world, that would have been obviously something that would have been addressed just for the scope of the project. We just neglected that.
All right, thank you.
This is Julio. I got a question.
Yes, sir.
Yeah, okay. In regards to existing traffic conditions, the original permit for Ave Maria had, some traffic generation done back there, and by different sectors and everything. So on determining the number of lots you can design in a sector of Ave Maria like this, in an area, specific area, I mean, that limit in the amount of traffic that you can generate from the new area might limit, constrain your number of lots. Do you take a look at any of that? Existing traffic conditions, pre-approved traffic generation versus what you could be generating from, having 120 or 100 or 130 lots, something like that?
So that is a great question. In terms of the transportation engineering aspect of this project, we settled early on that the scope of our project would mostly include utility and stormwater, as well as configuring the site plan to meet our lot size requirements. So we did not perform any transportation engineering calculations as part of this project.
Okay, yeah. My question was doing just to, these projects are the idea. One of the main ideas is to expose you to real life engineering applications, right? So, in real life, you will have to consider that, for determining the number, maximize the number of lots. Yeah, but if you generate more traffic than was previously approved, then it would not be possible. So I'm just making the point for that, okay? Try to help you out a little bit from that angle, okay?
Okay, thank you very much for your feedback.
So thank
Sure.
you. Maybe we move to the next team for the time being, and just learn from the next, from the brief first team. I want the second team ready with video, your webcam and your voice, so that when you speak, you see like Eric or things like that. So instead of hiding your camera, when you start, the first to jump in, you introduce yourself, and then you will start. So let's stop sharing the first team, and the next team, it will be Florida West Coast Engineering, and the mentor is Christopher Ordonez.
Okay, so can we start now?
Yes.
Okay, awesome. Hello, everyone. We are Florida West Coast Engineering. My name, and we've designed an intersection at Veterans Memorial Boulevard and the entrance at Veterans Memorial Elementary School. And to verify, it is a traffic signal. So shown here is the site, and in the red circle is where the intersection that we are designing is located.
Hello, my name is John Cressy. Florida West Coast Engineering was contracted by Collier County to improve the intersection of Veterans Memorial Boulevard and Veterans Memorial Elementary. We were originally going to completely redesign the intersection, but after speaking with our contact, we decided to just modify the intersection and develop a signal. Our contact from the traffic department is Christopher Ordonez, as our professor mentioned, and we will be discussing our communications with him in greater depth in a later slide. We've created 3 alternatives to enhance the flow of traffic and greatly reduce the risk of accidents through the intersection. The intersection in question, as it currently exists, is unsatisfactory. Traffic can be seen backed up down the road between 7:30 and 8:45 a.m., as well as between 2:30 and 3:30 p.m. These are generally the hours when parents are dropping off and picking up their children, as it's when school lets in and lets out, respectively. The intersection has no, as it exists right now, has no stop signs, traffic lights, or traffic directors, and this is especially dangerous given the proximity to the elementary school. A crosswalk can be seen, you may actually be able to see it in one of the pictures, just in front of the school entrance, which is designed for children entering from the nearby Sequoia Reserve community. And having these groups of unprotected children pass right through the intersection while traffic is backed up and everyone's rushing to get their children to school on time is a recipe for disaster.
Hello, my name is Austin Bouban. To better understand what needs to be done for the roadway, we began by analyzing the present effectiveness of the intersection. To do this, we need to determine 2 separate things, those being our 15-minute traffic volume and our normal traffic volume. Afterwards, we could calculate our peak hour factor, or PHF, in the PowerPoint. Values in between 0.25 and 1 are considered acceptable ranges, with 1 being the most optimal. To find our traffic volume and 15-minute traffic volume, observation of the intersection had to be done. After meeting several minutes before a known instance of high traffic flow, we continuously noted the number of cars headed up and down the road. During our analysis, we noted the total traffic volume at every 15-minute interval. At the end of our observations, we also recorded the total elapsed time and assumed that the intersection operated under first in, first out conditions.
Hello, my name is Eric Burgess. This slide shows the peak hour factor data that we collected at the site. from 7:30 in the morning to 8:45. As you can see from the table, 8:15 to 8:30 was the busiest time for traffic. If you take a look at the red arrow below the table, you can see that we calculated the peak hour factors to be 0.582 entering from the east, 0.25 entering from the west, 0.6 passing from the east, and 0.477 passing from the west. These numbers are a measure of traffic demand fluctuations within the peak hour. This next slide is on the queue lengths and delays that we calculated. The queue length is simply how many vehicles that cause a queuing delay. For this project, we found a maximum queue length of 4 vehicles and a total delay of 37.44. The maximum delay was determined to be 30 seconds. The 2 graphs at the bottom of the slide are the queuing results from 8 a.m. to 8:30 in the morning. This is where the number of vehicles is on the y-axis and the time in minutes is on the x-axis. Looking closely, you can see that the arrival curve is in blue, departure curve in orange, and the line to queue dissipation is in green. We talked to our client, Christopher from Collier County, and we're informed about the new high school being built to the west of Veterans Memorial Elementary, and that Veterans Memorial Boulevard would be extended all the way to Old 41 Road. To account for the increase in traffic, we assumed a 4-lane, 2-way road for Veterans Memorial Boulevard.
So I'll briefly summarize the 3 alternatives we created, and I'll allow my partners to explain them in greater depth in the following slides. Our first alternative was to create 1 westbound turn lane where a left turn can only be made on green. Our second alternative was also a single westbound turn lane, but with a flashing yellow arrow. And lastly, our third alternative was 2 westbound turn lanes and left is only on green again. Next, you'll see the AutoCAD drawings for these layouts.
Options 1 and 2 are pretty similar in design, consisting of a singular left turn lane and a traffic stop. Both of these designs have only one difference, this being that the left turn signal requires green to turn in option 1, and in option 2, the left turn signal is flashing yellow for yield.
All right, here's our option 3 layout. This is the one we ended up choosing. This is an AutoCAD drawing that shows the intersection having 2 left turn lanes going into the school instead of 1, and shows the 20-foot medians on both sides of the intersection. 4-foot wide bike lanes are included in the design, as well as a 10-foot wide pedestrian walkway that will allow plenty of students to cross at one time. All of the center, turn, and stop lines are drawn to DOT standards. Our team believes this is the most practical layout of the intersection to provide the best flow of traffic. This slide covers the cycle time and level of service. The cycle time is the time taken by a signal to complete 1 full cycle of iterations or 1 complete rotation through all signal indications. Cycle time is denoted by C, and for this project, we found the cycle time to be 190 seconds. The level of service, or LOS, is a mechanism used to determine how well a transportation facility is operating from a traveler's perspective. Typically, 6 levels of service are defined, and each is assigned by a letter from A to F, with LOS A representing the best operating conditions and F representing the worst. For this project and the design that we came up with, we found the level of service to be C.
As mentioned in the client feedback, if the volume of vehicles is more than 300 vehicles per hour, there must be a second turn lane. The school morning traffic volume turning left from the westbound lane was calculated to be 354 vehicles per hour, which means that the option chosen has to be option 3. This is also the option with 2 westbound lanes and a left turn on the green arrow only. Further considerations were made in regards to the radius of the connections between the streets. After doing a bit of research on the average turning radius of streets, we found that some information coming from the National Association of City Transportation Officials gave us what we needed. Knowing that the speed limit of the road, as well as the super elevation and our side friction factors, we were able to calculate the radii that we would use in our design. As seen in the figure, the westbound traffic has the largest queue times. In particulars, the maximum queue length is observed for both left turn lanes at 167 and 232 feet. On average, Both of these left turn lanes have a queue length of 140 and 171 feet respectively. Furthermore, their 95th percentile queue lengths are 172 and 246 feet respectively. In contrast, the westbound and northbound through traffic received the smallest queue lengths. For both, they actually had identical queue lengths for their maximum and average queue length. Maximum is 30 feet, while the average is 6. For the 95th percentile queue, the northbound has the least length at 25 feet. The westbound follows up with 26 feet.
All right. So we would have shown the flowing traffic via synchro, but since this is now an online presentation, it can't be done anymore. So instead, what we've decided to do is do screenshots of the delays per vehicle and the queues for all 3 options. So shown here is a synchro layout of option 3, which is the chosen option as stated earlier. So this is the date of the morning traffic only, because as mentioned before, also we couldn't go in the afternoon due to the outbreak. Due to the quantity of drivers turning left from the east, it is shown that drivers who are turning left coming out of Veterans Memorial Elementary and the drivers who are either turning right or going straight from the west have the biggest delay at 55 to 80 delays per vehicle. Having this means certain dimensions regarding time might need to be changed once the new high school comes in. Currently, there are only 19 vehicles per hour coming in that direction from the gated community Sequoia Reserve. So the queue on this option here shows that the 95th percentile queue length, which 95th percentile, it wasn't mentioned before, it's a queue length with only a 5% probability, and the maximum queue length on the outer westbound left turn lane are over 210 feet, which is the length of the westbound left turn lanes. The maximum and average queues are pretty much in appropriate places in all lanes, but the maximum on the left turn lane could probably be a little more improved though. All right, so now I will show you option 1. Option 1 would have been the worst choice out of the 3 options because it does not meet standards and the intersection would have more delays per vehicle. So if you look at the queue layout for this option, you will observe that the average queues and the 95th percentile queue lengths in both the straight westbound lanes and the westbound left turn lanes are long enough to cause constant morning delays. So opposed to option 1, option 2 would have been a great option. However, it does not meet standards and it allows for a level of service B, which is better than C, but is not economically feasible. So having a level of service B there is a complete dream. It's never predicted to ever be reality. The reason it's a great option is because it has the least delays per vehicle.
Steve, prepare to wrap up.
Okay, thank you. Although option 2 creates the least delay, the 95th percentile queue length in the left turn lane is not an appropriate length. This option would cause more possible delay than option 3 in the westbound lanes of Veterans Memorial Boulevard.
So in conclusion, we would officially recommend our 3rd option because it meets all FDOT requirements and provides the most efficient alternative of the 3. It also would greatly increase safety and reduce the risk of accidents in comparison to the current layout. Unfortunately, as Stephen mentioned, our layouts had to be mostly constructed from our morning traffic data because once the COVID crisis shut all the schools down, we were unable to go and observe the afternoon traffic, solidify our data because no one was coming to school anymore. Our client from Collier County has approved of the designs, and his department will likely construct something similar once the country reopens and construction on the intersection begins. That's pretty much it. Here's our references for the presentation and our formal reports. I'll just cycle through and give everyone a chance to see them.
Thank you, team. So we have 2 minutes
We have some
for the question.
acknowledgements. Sorry. Lastly, we'd just like to personally thank Mr. Christopher Ardones, our contact from Collier County Growth Management Department, Dr. Villers, and Dr. Long of UA Whitaker College for their assistance in completing this project. And that's it. Now, any questions?
Very quick question. Did you consider utilizing the signal unit Does your study require any signalization for the intersection?
I'm sorry, could you repeat the
Sorry, I
question?
couldn't hear that.
Does your study or your project require a signalization intersection?
Yes, and we actually have the constructing of the signal all in our project schedule. And yes, we did take that into consideration in the project pretty much. But
okay. Thank you.
Yep.
Thank you, sir. Any other questions?
Just a quick question. Just an observer. This is Dr. V. Very good work, guys. I just noticed that in your option that you're selected, you have the lane width as 10 feet. And I don't know if it's the actual value or if it's a typo.
I think it might be around like 10, 11, something like that.
And was that also there in your analysis? That was the width of the lane, and why did you select 11 or 10 feet? Is it because of the right here? Is that because of not enough right away, or because 10 feet is a lot of stress in the system?
Well, currently the lane width is like around, I measured it on Google Earth. The lane width is actually around 10 and 11 feet on Veterans Memorial already. So we just assumed that and went from there.
Thank you.
Yep. Yeah, thank you, Dr. V.
Yes.
Thank you, Dr. V. Can you stop sharing the team? And
yep.
The next team is JAMB Engineering. Project E Area GS10 Land Improvement in Lehigh Acres, and mentored by Steve Neff. And share your screen and start. Julio. Sorry, Javier. Perfect. Yep. Go ahead.
Okay, so our project was on area GS10, and it's for land improvements, and we are JAM Engineering. All right, so a little bit of background about the site. The site was previously used for mining, and it's abandoned, and it's under the Lee County 2020 conservation. And based on reports from 2019, there is no contamination. All right, some of the problems. During Invest 92L and Irma, there was a lot of flooding in the area. So we're trying to mitigate the flooding and in that area. There was significant flooding in canals, roads, and buildings.
So the design objectives for this project were, one, to control the flood mitigation. Javier said there was significant flooding that was causing issues with residential and commercial areas and the canals. And the objective is to control water quality within the basins that we have designed.
I'm not hearing anything.
She's muted. Ashley, I think you're muted.
Can you guys not hear me? My thing is not cooperating. So the existing conditions and constraints for this project area are residential and commercial flooding, the poor water quality with the standing water that is existing on the mining site, wildlife habitat within the site, cypress trees, and wetland preservation. These constraints were taken into consideration when designing the 3 objectives that Mitch is going to talk about later on in this project.
My name is Mitchell Grant. This is a map of the various watersheds throughout East Lee County that serve the purpose of providing insight on the area in which our project would have a direct impact on. It further aided in understanding where the flow of water leaving the system would have to travel before eventually making its way to the Caloosahatchee River, making us conscientious of the importance of water quality treatment. Ultimately, it helped in finding the approximate area of Section 10's basin to further aid in runoff calculations. As part of the design criteria, we were tasked with coming up with 3 different design options. This allowed us to weigh out the pros and cons of each and then selecting the most beneficial and feasible option that is in line with our goals. Alternative 1. This design option includes the excavation of 2 large separate stormwater reservoirs. The system would collect stormwater runoff and rainfall naturally. There are no inlet or outlet structures. Alternative 2. This design option includes the excavation of 1 large storage reservoir. The system collects stormwater runoff and rainfall naturally, and there are 2 outlet structures that control the flow of water out of the system. One sends water to Greenbrier Swamp to the north, and the other to Fox Canal to the west. Alternative 3. This design option includes the excavation of 2 separate large wet detention ponds. The system collects stormwater runoff and rainfall naturally and through canal inlets. The inflow of water from Easy and Kings Canal is regulated through inlet structures. Flow from Basin 1 is transferred through the filter marsh and into Basin 2 using gravity flow. 2 outlet structures control the flow of water out of the system into Greenbrier Swamp and Fox Canal. We wanted a system that could accommodate both water quality and water storage, so we decided to choose option 3.
This is the option 3, the one we went with, and we made the calculations. You can observe the filter marsh, and it was designed based on the gravity flow. The total length of the filter marsh is about 2 miles. And for each section, I don't know if you see my pointer, for each section, there is about 1 foot drop in elevation, which will give a smooth gravity flow. And the water gets into the basin 1 through the Easy Canal and moves into the second basin through the filter marsh or through the outlet control structure situated right here, and goes out in the Fox Canal through the existing canal, or it's directed to the Greenbrier Preserve via a culvert pipe that will need to be calculated. We didn't do that yet because there are a few roads there that cannot be disturbed. This is the section of the wet detention basin, and you can see the permanent pool depth. We calculated that. This is the control structure. This is the 25 years storm event elevation and the 100-year storm event elevation, a 4-to-1 and a 2-to-1 slope for the sides.
Okay, and this here is our outlet control structure. As you can see, we designed it with a outlet pipe of a 24-inch diameter, the orifice 12-inch diameter, and as you can see here are the lines for our 25-year event storms or our 100-year event storms. And also the size for the weir, we calculated it to be 108 by 36 inches. And here we have the berm that's going to go around the basins. We did a 2-foot height berm with a 2-to-1 slope on the sides.
To calculate the permanent pool volume, I used the modified rational method and not the rational method, because the second one, it's using the storm duration, it's different than the time of concentration, which gives a a lower peak flow and a larger volume, which we need to make sure will accommodate the Hurricane Irma runoff. So we come with a permanent pool volume of 2,073.5 acre feet. And the table below, it's the land use. We break down the whole area per land use and hydrologic soil group to calculate the composite curve number for the hand calculations.
In order to account for water quality, you guys can hear me, right? We're good? Yes. Okay. In order to account for water quality within our project, we used BMP trains. The watershed characteristics that were used for the software was the catchment area of 4,700 acres with a contributing area of 3,760 acres. This is due to multiple wet ponds throughout the catchment area. In the previous slide, you saw how the composite curve number was calculated. That curve number was used for this software as well. The rainfall zone that this GS10 falls under is the Florida Zone 4, and it has an average annual rainfall of 54 inches. I don't see my slide. Okay. The wet retention design, we used the same permanent pool volume that was calculated of 2,073.48 acre feet. That produced a permanent pool volume for 31 days residents of 546.1 acre feet with an annual residence time of 118 days.
We kind of lost her.
Seeing if the nutrients were removed within our design, we used the consideration that 10% of the pre-development nutrients needed to be removed. This is the load diagram for the wet retention area alone. As you can see, the nitrogen and phosphorus system.
For the cost of the project, since it's such an elaborate project, and we didn't have the means to calculate the total cost, but we know that the excavation cost is the biggest one. We calculated that, and we come with a total of 2.25 million loose cubic yards for the basin 2 and 1.2 million loose cubic yards for the basin 1. And the total cost of the excavation will be around $20 million, a little bit over $20 million.
Okay, so to conclude our presentation, with this project, there's little to no impact on the environment. We are keeping wetlands intact. We are incorporating more vegetation, obviously through the filter marsh, and the flooding was controlled and water quality was improved. So all in all, the project was a success, and this concludes our presentation.
Perfect.
We gotta go to acknowledgements. Wait, acknowledgements. We have to thank Dr. Nguyen for guiding and supporting us through our final, well, one of our final classes for our senior year. And we want to thank Mr. Stephen Neff for mentoring us and answering all of our questions in our emails regarding this project.
Thank you. So we have a few minutes for Q&A.
Okay, a couple questions. Question one, can you hear me?
Yes.
Yeah.
All right. What did you, your berm, when you design your berm around your retention system, what did you design it for, the 25-year or the 100-year?
25 years.
The 25-year storms?
Yes.
And that's when, all right, and that 2 feet, you said that the depth of the berm is 2 feet, that will give you the 25-year storm elevation? Go ahead.
The pond can accommodate enough stormwater for a 100 years event, but we designed the berm for 25 years because we don't need such big berms since it's already taking into account within the pond volume.
Okay, but the lake was designed for the 25-year storm to contain the 25, so there's no reason for the berm?
No, it's no reason for the berm. We just designed the berm to use some of the excavation dirt, so we don't have to haul away a lot of dirt.
Okay, do you have a geotechnical data on the site to see if there's any rock, and the cost of the excavation may go 3 times much higher than if you have rock? Do you have any geotechnical report?
No, no.
Yes. All right, thank you.
Thank you.
We have time for one more question. Okay, so let's thank you, team, and let's move on to the next team. JAMM Engineering, Central Orchard Land Development, and Bonita Springs with mentor Miss Fissinger and Mr. Barber.
All right. Next here, everyone else is here. Can everyone hear us?
Yes.
All right, so we are JAM Engineering with JAMM, instead of the previous group, JAMB, not to be confused. We did our senior design project with the mentors, Agnoli, Barber, and Brundage, myself, Justin, Gus, and Marty. All right, so our site was located at 8991 Strike Lane in Bonita Springs, just east of 41. Highlighted in red shows the 15-acre property. Our effort to build this into a small residential community while maintaining as much of the existing orchard located at the center of the site. We were tasked with designing the utility infrastructure, preparing construction level, and completing all necessary permit applications. This image shows the existing infrastructure that we would tie into. Our site is located right here. You can see in blue is the 8-inch PVC water main. In green is our existing wastewater piping. We had an existing lift station that we would tie into. And at the bottom center here is our community dry basin that we would tie our stormwater runoff into.
And as you can see, this is our existing conditions photo from our site plan. And as you can see, it's a long, narrow plot of land in Bonita Springs, which really limited our design options that we had. And on the site, obviously, Max said it's a 15-acre organic orchard, which needed to be maintained as much as possible. And there's actually a canal located on the western half of the property, which limited our design even more. And on the next slide are all of our designs, option A, B, and C. They all featured 13 or 14 parcels, ranging from a 1/4 acre to 3/4 acre lots. All 3 design options had a orchard park to maintain as much as the orchard as possible. And option A actually had 3 pedestrian bridges to access the future rail trail on the other side of the canal. And option B had a cul-de-sac at the end of the property.
So for our final analysis, we took each of those designs and thought about the benefits that each had as well as the disadvantages, and composed this table that you can see in figure 8. Looking at the advantages and disadvantages of the design, we thought of for our final design, what would maximize our profits at the end of turning our plan set over. So we took 5 of these things into account, which was the technical, financial, time to complete, environmental, and societal aspects of the design. And then for our final thing that we just came up with was a official construction plan set. So figure 9 is the cover page of our plan set. And on this, so we came up with 20 sheets, and that is what you can see in the sheet index. The aerial location map is basically the southern part of the property, and that shows the entrance to the property. vicinity map, shows where the property is located in the state of Florida, prepared for, as well as zoning. And those boxes indicate further details for the project, as well as specifications of the parcel itself, and then a legend. So as we go through the plans, specific things that we're going to talk about, this legend talks about what, or indicates rather, what we called out in the plan set.
Here we have the master single family site plan. This plan is located at the beginning of the neighborhood, and it represents an idea of what all the lots will look like. As you can see, each parcel is about 0.75 acres. The one-story single-family home is 2,600 square feet, and is placed within the required setbacks, which are 25 feet in the front and 10 around the sides and back. We also added in a 24-foot wide driveway for house access.
Okay, so this image shows the paving, grading, and drainage site that we developed. There are 7-foot wide swales on either side of a 20-foot road. On the east side of the road, we have a 6-foot wide sidewalk. Okay, the lots are designed as split drainage at the very south of the property, which is right here. The swales, we designed 2 drainage structures to direct the stormwater runoff off of the property. So here are the drainage structures at the south side of the swales. And then those would tie into that dry detention storage area that we saw at the base of the, or at the south of the property, and using a control structure to regulate the proper drainage from the site. This shows an example of that pedestrian bridge that we talked about. Part of the scope of work was the rail trail, the future rail trail at the west of the property. And since we did have that canal there, we wanted to make sure that we would have access to that area rather than having to go all the way to the south of the site. So we proposed having 3 different pedestrian bridges there. This kind of shows an example of what that would look like. And then here, this is the north of our facility, and this is where we designed a hammerhead to comply with the fire safety code to allow a turnaround for fire trucks and first responders.
So for the water main design, we decided to go with an 8-inch water main, which, in accordance to the Bonita Springs Muni Code, fit the required flow that we figured we would need for the residential properties, and also a 2-inch service connection from the water main to each home.
Also on this plan is there's utility plan. We're calling out the gravity-fed sanitary sewer main, which was proposed to be designed and installed. The sanitary sewer main is running down the middle of the road that will be installed. Like we talked about earlier, there was existing sewer and water mains already established. So to the left of the plan, or far south of our property, there's an existing lift station, and that's what our gravity-fed sewer main would tie into. Each property, or so 14 of the lots, each of those lots would have a utility sanitary sewer line fed to them, which would be 6 inches, and the main itself, or sanitary sewer main, would be 8 inches. All of this is called out. So, like I said, it was all called out, and this is now looking at the far north end of our property, and how we came up with the slopes of the sanitary sewer main. The main would have manholes approximately 400 feet between each, and the diameter of the lines. All of those were found in the Bonita Springs Utilities Standard Specification Handbook, found on the Bonita Springs website. It was important to follow these guidelines. Figure 17 in the upper right-hand corner of the slide is basically a profile view of how, and explains the calculations that were processed to determine how deep the pipe needs to go in the ground. So, and like I said, the slope, there was a 0.4% slope of the sanitary sewer line.
For each service. Go ahead.
So for the last bit of our plan set, like I said, a lot of the sheets that we developed, we cut for the sake of this presentation, but these sheets were very important. They're details. So things like your clean outs on your sewers, your water meters, your precast manholes, your manhole covers, and others, they all have specific requirements that City of Bonita Springs requires you to install. So that's what these drawings, as well as two other sheets that weren't provided in this presentation, are illustrating. So the idea is that we would turn this plan set over to a contractor and a developer. If a contractor were not to follow these details and install equipment that didn't follow this, when it came time for the contractor to turn over this residential community to the City of Bonita, the City of Bonita could deny the rights to maintain and provide upkeep for these services. So by following these details, that could prevent hassles down the road. And then our final plan set was the erosion control detail. So basically, before any ground would be constructed on the property, these erosion control measures need to be established. So your construction entrance, your silt fence, which, whenever dirt is moved around on the site to prevent it going into neighboring properties or neighboring lands, silt fence needs to be established. And if there's any existing storm grates, putting in sod around the storm grates prevents soil from getting into the storm system and clogging those pipes, which could be, once again, a hassle. And then at the bottom of the screen is a viewport, basically an image of our overall property. And this shows where the silt fence would be installed, which is basically the perimeter of the property.
Moving to the cost of the design, this is an opinion of probable cost sheet. It gives us an idea of how much this design is going to cost. It also shows us how much of each material we need. It's split into 7 main categories: water system, sanitary sewer system, paving, grading, drainage, landscaping and irrigation, and a miscellaneous section. All these categories totaled to about $840,000. We then took into consideration a 10% contingency, which brought it up to $92,000. Then there was also an extra 10% for a design permit, and then 10% for permit review fees, and 1% for bonding. Our grand total came out to roughly $1.12 million. And then this is just a cost summary of our design, looking at the 7 main categories we had and how much each of them cost. The sheet also shows us the extra costs, like the contingency and the design permit fees. Once again, the total cost was $1.12 million.
So in conclusion, we came up with that if we sold each home for $350,000, and we would net a net profit of about 3.4 million, which we determined that this development was a viable project that could actually be constructed. And we would just like to say a big thank you to Tom and Kelly Fissinger from Agnoli, Barber, and Brundridge for taking all the time that they did out of their busy schedules to help us with our project, and we really appreciate it. And there's the references.
Thank you, team. So back to the judges, if you have any question for JAMM Engineering.
Okay, one good presentation, thank you. One quick question: when looks like you run about 3,000 feet of water main all the way down to the cul-de-sac, and I'm assuming that would be your last fire hydrant. Did you do any hydraulic calculation, make sure there is any water comes out of that fire hydrant?
No, we didn't do any hydraulic calculations like that. We did do calculations for each fire hydrant, but none like that, no.
Okay, thank you.
We have time for one more question.
Hi, I saw a finished floor elevations on the house sites. How did you determine the finished floor elevations?
So I'll take that one. The finished floor, we found the existing site elevation was around 12 to 13 feet. And then based off of that, Bonita Springs municipal code is where we determined that, you know, the finished floor had to be a certain distance above that, that site elevation.
Thank you.
Thank you, team. So from Bonita Springs, we move back to Naples, 2TS Engineering interchange at I-75 and Vanderbilt Beach. Mentor Julio Ordonez.
We got everybody here?
Yes, yes.
Okay. So good afternoon. My name is Jason Young with TOTS Engineering. We have been working with Julio Ordonez and the Collier County Growth Management Department to assess and provide a geometric layout for a new intersection at Vanderbilt Beach Road and I-75.
Hi, I'm Holly Hurlbutt. I'll begin with a little background information on why we need this interchange here. Collier County has a population of about 382,000, and it's continuing to expand, develop, and urbanize. And since 2010, we've seen a 17.4 increase in population, and with this future growth, Collier County is on its way to becoming an urbanized area. Currently, we are experiencing heavy congestion at Immokalee Road and I-75, as well as Pine Ridge Road and I-75. This is due to the limited access to the interstate in these areas. So due to the growth and development of East Collier County, Vanderbilt Beach Road will be expanded, as shown by the orange area here. This land is designated by the Golden Gate Growth Management Plan as a residential development area. And with the expansion of the population, we'll need to have access to the interstate here. And Vanderbilt Beach Road only currently goes till about Collier Boulevard, and then it's planned to be expanded further east. So with the future growth of the population and the development of both residential and commercial areas here, it'll provide a large need for the interchange here for I-75 and Vanderbilt Beach Road. So as Jason had briefly mentioned, our objective was to analyze the feasibility of this I-75 interchange at Vanderbilt Beach Road in Naples, Florida. And this was really done, we considered current traffic patterns, community impact, surrounding environment, preliminary costs, all associated with this interchange.
Okay, so to study the traffic data, first we were looking at FDOT's Florida Traffic Online and Collier County's traffic counts. Now the interchanges north of Vanderbilt Beach Road is this one you see here is Immokalee Road. It sees regular congestion and delays due to the high volume. As you can see here, you have the on-ramp to I-75 North is an average annual daily traffic of over 19,000. And we calculate at peak season, it can get over 2,700 cars per day. This is I-75 and Pine Ridge, which is the intersection just south of Vanderbilt Beach Road. It's similar as the makeup, but it obviously is a little less. The northern entrance, the northbound on-ramp and the southbound off-ramp for both of these intersections controls about 67% of the traffic in that area. Vanderbilt Beach Road is not connected at this time. As you see, we have calculated peak hour rates of 2,600, or I'm sorry, 2,300 and change, and our physical counts though from January averaged out to 2,608. Of special note, we looked at Oaks Boulevard. this connects Vanderbilt and Mockley Road there. There is no light at Mockley Road on Oaks, but there is on Tarpon Bay just to the west there. The really particular on this one is the counts for Oaks Boulevard southern area, which has 7,000 cars per day more than the northern part of this road. So it indicates a lot of people moving from Vanderbilt to take that left turn at the light to get onto the interstate.
Hi, my name is Christian, and I will talk about the constraints that need to be considered for the design and the final selection of the interchange. First, I-35 has 6 lanes going south and north with an average width of 12 per lane, but it will expand to 8 lanes as it already has in some areas, according to plans of the I-75 Southwest Connect project. Now for Vanderbilt Beach Road, the average lane is about 11.3 feet. It has 6 lanes going west and east. There is a median of about 8 feet and an overpass with a clearance of 16.3 feet. Sidewalls are present in both directions. With the dimensions, we have come to the conclusion that it's possible to have 2 turning lanes coming from the northwest ramp of I-75. In order to design which type of interchange will work better, we took into consideration the proximity of the highway to populated areas. In the northwest, the Wilshire Lake community extends along the I-75 with an average separation of 120 feet. Consider the embankment slope, it leaves us with only 75 to place the ramp. In the southeast area, the village wall of Naples is close to I-75, but there is enough space to work. Plus, there is already a noise wall in place. The canal on the east side needs to be covered in order to complete the ramp. The biggest concern is how this will affect the hydrology of the area and whether or not it can be mitigated. In the southeast, that is the Vineyard Elementary School. This represents a safety concern as there will be vehicles moving at considerable high speed close to the baseball and soccer fields.
So our team initially brainstormed 3 different solutions to determine which would be the best fit for our interchange. The first proposed solution is having a middle off ramp for the southbound lanes. So this ramp would be a left exit off of the southbound and enter Vanderbilt Beach Road between the 2 overpasses. The other ramps would follow the standard diamond interchange. This design would really require retaining walls right there on the insides of the overpasses, and it would allow for less private property to be acquired, especially on the west-hand side. Unfortunately, the future proposed expansion of I-75 may prohibit this design, and overall, the estimated cost of this design would have been about $56.81 million.
All right. Hey, everyone. I'm Jacob, and I'm going to talk about our next solution, which is the tight diamond. It's an approach that's common to densely populated areas because it requires minimal land use. We estimated about $46.5 million in construction costs, making it considerably cheaper than our alternatives. The limited area on the west end of I-75 would require retaining walls necessary for the embankments at the exits located here. We would also need to implement signalized intersections, which would be placed on either side of I-75. However, with only 200 feet for the southbound turn lane and 400 feet for the northbound turn lane, we may see traffic that overflows into the through lanes.
Our third design was a southbound flyover. The exit and entrance ramp to the southbound lanes exit to the left of the flow of traffic. They overpass the northbound through traffic and come together at a single point urban interchange at the east side of the interstate. So this is our only design that actually allows adequate distance for our storage lanes for our left turn lanes onto I-75. The total cost, however, on this one is about $152 million. So it's 3 times more roughly than all the other designs here. There are a couple of common requirements for each of these designs. The first thing we're going to look at is the movement of our intersection at Oaks Boulevard. Currently, there's a light there, like I mentioned before. For adequate flow through all of the traffic lights, we would recommend closing this off and creating a new road here at Vineyards Boulevard into English Oaks Lane. Now, this would close off or at least remove the lighted intersection that allows access to the Vineyards Elementary School and the connected fields there, but they do have access already through Vineyards Boulevard.
So by replacing the existing embankment slope with a retention wall, it will allow us to move further away from the communities. So it will not be necessary to build a noise wall or to acquire land. The run can be as close to the I-75 as needed. The retention wall can cost up to $3 million on top of the construction of the interchange. The gravity wall is the best approach for the retaining wall, as the height needed goes over 16 feet. As is shown in the first drawing, the distance of the slope is 42 feet, close to the community. But if we were to include the gravity wall, we can move around as much as possible close to the I-75, as is shown in the drawing. It will allow us to keep the same number and the width of the lane, but with the advantage of a bigger radius of curvature.
At what time, I'm sorry?
Or semi-trailers with a span of more than
3 to 6, okay. Oh yeah, we'll see you then tomorrow. Thank you very much.
All right, so focusing on the environmental aspects of our design, the biggest challenge that we faced is the canal located on the eastern side of I-75, which is shown in the picture to the right. It extends about 2 miles north to south where it feeds out into another canal. And the exits east of I-75 would overlap this existing canal, so we would need to implement a culvert to cover that up. We chose a box culvert for our design that would extend a half a mile north and south of that relative intersection. Moving on from the canal, as it relates to this next topic, we're going to discuss the retention area that's located in the southwest corner of the intersection as shown. The entrance ramp at this location would directly interfere, similar to the canal, also requiring us to cover it. It's about 10,000 square foot area. Another impact that we would have by, on this interchange is going to be the existing sidewalks. They would interfere with the ramps that would be installed. For that reason, we would need to implement appropriate crosswalks at the locations that are shown in the image. There will be signalized intersections, as I previously stated, on either side, so a walk signal will also be included. However, you won't see any pedestrians crossing Vanderbilt Beach at this location. So, this is just the technical considerations that we used for our design. These are all from the Florida Department of Transportation Design Manual, and they were the considerations that we used to generate some of the final data that we got. And this is just a brief overview of what we've already discussed. For our final design, we decided to go with the tight diamond. It's going to feature 4 lane off-ramps with directional islands and retaining walls as mentioned due to the limited area. The canal east of I-75 will also be covered with the box culvert as mentioned, half a mile north and south. We will also remove the intersection at Oaks Boulevard where the traffic will be rerouted so it can keep the connection with Vanderbilt Beach Road. And this is just an image kind of depicting the traffic flow for our final design that we generated. And you can see that in front of you.
Prepare to wrap up, Jacob.
So considering the cost and scheduling of this project, we looked at the research and development, designing, planning, permitting, and construction aspect of this project. And we determined that it would cost approximately $66 million. And then we also estimated about 102 months or about 8.5 years from start to finish for this project. We would like to thank everyone for taking the time out of their day to learn about our project, and a special thanks to Dr. Nguyen, Julio Ordonez, and Dr. V for their help and contributions to this. Thank you guys. If you have any questions.
Thank you, teams.
So if you have any questions, we're here.
No questions, just to say, it's Julio. Just to say, I'm impressed with the final product you presented. His recommendation is really nice. It makes sense. Congratulations, guys. Well done.
Thank you, sir.
This is Dr. V. So I see the alternative was mainly selected, especially on the cost. I know you did some analysis using Senko. And by the way, very good presentation. Very proud of your guys. Did you look in all the alternatives, something like delay or level of service? Or if so, how did that match with the selected approach that you have?
The synchro, I did most of the synchro, but the due to the outbreak and everything, I did not get a chance to really get as far into it as I wanted to. The initial look was well, initially when I put it in there, I was getting like level of service G and H, but once I moved the intersection from Oaks Boulevard over to Vineyards, it actually improved a bit. I was getting B's and C's, but I don't have all of that information, and I don't have access to that information now to finalize it on this report.
Thank you.
Any other questions? Just to let the judge know, we have only 2 programs installed in 6th floor on our campus, and due to the pandemic, some teams have difficulty to get into the building and run the simulation in the final design. They did that at the beginning, but then difficult to test at the end. So see, we have no more question for TOS team. Let's move, still keep in Naples, South Florida Land Development team.
How you doing?
Good, good. Go ahead, Brett.
Actually, I think Justin's going to start us off.
I'll start it off. Hi guys, I'm Justin, part of the South Florida Land Development team, and we're doing the Golden Gate Senior Expansion Center. We partnered with Ayub and Claudia at Collier County Facilities Management Division, and they were a big help along the way. Our objectives were to create a 6,000 square foot building that had bathrooms, water service, sanitary service, site drainage, and a lift station analysis. This building is going to be used to connect the existing library and the senior center. A little bit of background: the current senior center was once the library. The old library needed an expansion as the surrounding area grew. So instead of expanding the old library, they just built a new one right next door. The new library provided better opportunities for growing technology. The old library was a place where seniors could now gather for events and socialize. They also provided healthcare for those in need. A third building is going to be constructed to connect the 2 buildings, and the new building will have conference rooms and bathrooms. These rooms can be utilized by the senior center and the new library.
Can you guys hear me?
Yes, sir.
Okay. What you see on your screen now is going to be an aerial image generated by GIS. It's going to point out the Golden Gate Library as well as the Golden Gate Senior Center that are currently on site. This is an accurate aerial image as there's only landscaping behind the current existing buildings. I'll go to the next slide. So this is going to be the existing conditions plan. We drew this up in AutoCAD 2020. As you can see, we have some existing pavement with existing parking spaces, which we will get into later in the presentation. We have existing pavement as well as the 2 existing buildings. The concerns from this plan, looking at it initially, was the on-site pump station and the existing light pole that's located between the 2 buildings. If we go to the next slide. this is going to be our master site plan. This is going to show us the proposed building, which is going to be about 6,000 square feet. It is going to be located directly behind the existing senior center, which ties into the existing library as well as the senior center. We decided to show the existing dry detention area because it is very important to treat the stormwater that falls onto the site once it does rain. We'll go to the next slide. The challenges that we came across through the design process and through the drainage specifically is where we tie the inlets in. When water falls on the site, it currently just kind of sat on the grass. It didn't really have anywhere to drain, but now that we add this impervious area to behind the existing buildings, we had to figure out where the water was going to go. So if you go back one slide, we decided to tie in to the southeastmost inlet. It's going to be right. It's going to be right above the dimension line, 24 foot dimension line in the existing asphalt. We decided to tie it into this area because we thought that it would find the best path to the detention area with the least amount of resistance and water stacking within the pipes. We can go back to forward. The next challenge was to grade the site to flow to proposed pipes behind the existing buildings, as well as the existing landscape. We had to work around the existing trees, existing grass, everything on the site behind the buildings, and we had to account for the building placement. We can't just throw a building behind the existing building. We had to follow the developmental code in Collier County to make sure that it is 25 feet away from the existing buildings at all points, as well as avoid the existing lift station on site. If you go to the next slide. These are going to be the ICPR nodal maps. On the left, you'll have our pre-development nodal map. The orange squares are going to be the basins, the manual basins. Those are going to contain information on the land use breakdowns for each sub-basin. The sub-basins were divided according to the existing inlets on site, and the blue circles are going to be the nodes. Those are going to be stage area nodes. Those were calculated using the aid of AutoCAD. Those were inputted with areas and elevations of the existing inlets. As you can see on the right, our post-development ICPR model looks very similar to our pre-development model. The only difference is going to be in the south. There's going to be a new pipe that is proposed to tie the proposed building area into the existing stormwater map. Go to the next slide. These are going to be the ICPR results. So the two important elevations to look at are going to be the detention areas in all 4 different storms. So on the left, we have our pre-development storm for the 25-year 24-hour storm and the 100-year 72-hour storm. The first important storm we're going to look at is the detention area for the 25-year 24-hour storm. As you can see, it stages to an elevation of 11.55 feet. This was originally thought to be wrong when we were running the pre-development ICPR model, because generally the 25-year 24-hour model is supposed to stage to the berm elevation. The existing berm elevation is at a 12. Now, when we were looking at the record drawings, we noticed that whoever designed the plan originally decided to account for a new proposed building, which is also 6,000 square feet. So that shows our group that they were already accounting for this additional impervious area. So we went with the 11.55, knowing it was going to stage higher. So if you look to our right on our post-development ICPR, we're going to look at our detention area for the 25-year 24-hour storm, and you can see that the maximum stage is 11.96. This is approximately 12 feet, so we assume this to be right, and that is how we know that our site is draining properly. Another indication that our site is draining properly is looking at the other nodes, S1, S2, S4. Those are all existing inlets on site, and those already have elevation of about 11.34, 11.4, all the way up to 11.75. So if you look at that, it's only staging to an 11.96, 11.97. So you can see that there's only a little bit of water on top of the existing inlets, showing that it does drain properly.
So in order to make sure that we had enough parking for the new building that we proposed, we obviously had to do some parking calculations. So we took this from their code, and with our calculations, we had plenty of extra space, so it wasn't any worry with adding the extra 6,000 square foot building. So with grading the site, like Max had mentioned, we really had to be careful with getting the water away from what was already there. We had to propose a swale between both the library expansion and the existing senior center because the finished floor elevations were at different elevations. And we also proposed a swale along the back of the library. So we used 11-yard drains with 12-inch PVC pipes to collect the extra water to route it to the existing stormwater inlet that Max had mentioned. So in order for us to connect to that stormwater inlet, we do have to demo part of the existing driveway into the property, and it would require about 750 square feet just to be able to do, we calculated it using 15 feet on center for dewatering and for just allowing extra room to place the proposed pipe. And we found this to be a better solution than going to a different inlet. So on the screen, you can see our proposed layout of the piping. Our proposed swale elevation stayed current between the buildings because they're set at equal elevations. So that proposed swale does stay at 12.8 to help collect the water. And there is an existing swale along the back that we were able to tie into and set our yard drains. We did also propose a second, our own catch basin, and we set the invert so that there's a 0.2% slope down to the existing, which we could see was used on the previous design. And if we go to the cross sections. So cross section A is between the two buildings. And this is standard throughout. So I was able to show that it's a 10% grade from the proposed expansion to the swale, and then it's 8% from the existing senior center. For the expansion out to the existing sidewalk and the roadway, it is a steeper slope, but it varies throughout. So the steepest slope that I had was about 20%, and other places it was closer to 8, just because we were going from elevations of 14 down to some that were like 11. But we were able, I felt that that was acceptable. And there's existing landscape in that area.
Hi everyone, Dylan here. So another task we had was ADA compliancy, because it is a senior center with handicap needs and whatnot. So our task was to design by standards the connection between the two buildings, because the one was at 11.9 or whatever, and the other one was 14. So we needed to make sure it was a 12-to-1 slope between the two, and we need to find a place that we could fit it between the buildings that would look good and work well. Here's just the simple ramp calculations to get the slopes and the total length that we needed. ADA compliancy does require like a 5x5 resting platform between the two if it goes over a certain length or distance of a slope. So we had two options here. We didn't really need the 5x5, but it would assist if, since this will be traveled a lot by seniors and people that might have disabilities. The best option probably would be option B. We see that the 6.6 and 6.6, this will be at 12% combined, and this here would be at 12% as well. And then right here is the proposed connection. Here is the senior center now, the expansion, and the library. So here you see, this is just depicting the option B. And yeah.
All right, guys, so this is, what's that?
Okay, you have 1 or 2 minutes.
Yeah, okay, I'll wrap it up. So there is an on-site, you're welcome. there's an on-site pump station, and it is privately owned and not maintained by Collier County, which made it a little bit tougher to get a hold of the owners and whoever maintains it, because when we go to do an analysis and to measure the pumping rate, what I would have personally rather would done was a pump down test at the site. However, we weren't allowed to access the site or access the lift station, but they did eventually get back to us and send us a detail sheet. And the detail sheet gives us a system curve, and it shows us that the pumping rate from the manufacturer, given the head elevation and everything, at the best possible outcome was 44 gallons per minute. It is typically lower for a 2 horsepower pump. However, this pump is a grinder pump, so it's designed to grind up solids coming in, whether from it's usually placed outside correctional facilities or rec centers and stuff like that. So it's not usually to displace the more flow, but to pass the solids. So when we weren't given, or we weren't allowed to conduct a pump down test, we just had to use the best possible pumping rate. So to do this, we usually just start very simply. We just find the pumping rate of the on-site pump station, which we decided was 44 gallons per minute. We analyze the inflow of the senior center and the library, and then we also calculated the additional flow provided by the proposed building with the 2 bathrooms. At the end, we just compare the inflows after the proposed building with the existing and a new pumping rate, and we can find which one either can handle it or can't handle it, or which one proves better. So go to the next slide. Next one after that, please. I actually have access to software with ABS Solzer, and I was able to choose a pump. This pump is also a grinder pump, so it matches the same function. It's relatively the same horsepower, but it does, however, produce almost twice the amount of flow with the given head. Next slide. Now you can see here, the reason I just did this GIS map just to quickly show the wastewater treatment plant to the blue circle, which is where our senior center is. Now it's not a very far to pump the wastewater treatment plant. There's definitely farther, but for a tiny pump like this, it does get manifolded into, but it doesn't pump on its own to the wastewater treatment plant, but it does connect later on down the road. Next slide. This Google Earth picture just shows the wastewater treatment plant currently in Golden Gate. If you look closely, you can see the connections on the tanks. They are relatively high in the air, and we know that our pump station is around 12 feet below the ground, 10 feet, I think it was. Next slide. And that difference in elevation actually gave me the basis for my system curve, which is this blue line on the graph. We know that when there is no head or no flow, there is actually a total dynamic head of 40 feet. So this shows in red our existing pump, our old pump, and how much flow we can imagine or assume with the head as it goes. And the green shows a drastic increase, I think. And I use the 10 state standard, which is per Collier County design criteria, to find a peak hour inflow of 4.42. And you compare that with the average gallons per day, which gave me, I think, 3 gallons per minute. Next slide. A lot of things we can analyze whether or not one was better than the other. The way I decided to do was to find the actual total amount of pump time it would take to pump down the total volume in the pump station. So with the old pump, it would take me around almost 6 minutes, which is a long time for a little pump to be pumping. And with the new pump, it was around 3 minutes, which is not great, but it's a lot better than the old pump. So in conclusion, I think the old pump really needs to be upgraded, especially if they plan to expand more in the future. Even at best conditions, it can't keep up and is halfway up to par with the new pump. I also would recommend selling the station to Collier County and having them maintain it, because they can take a lot better care of it, and it's a lot better on a monthly rate. And we don't have to worry about the red light coming on all the time. So that pretty much sums it up. We would like to thank Ayub and Claudia for helping us every step of the way. They have been extremely helpful. And of course, Dr. Wynn for everything he's done. So we're open to questions.
Thank you. I forgot mention the mentor at the beginning. So the mentors for this project is Ayub Abahu and Claudia Broncoroni. You guys went out a few minutes, but I think with 5 members is justifiable. So we have for 2 questions or something for the team.
I really enjoy it again. Once again, I enjoyed working with your student, Dr. And
Thank you.
I'm looking forward for another successful project. Congratulations, guys. You've done a marvelous job. Well, just watch your time. Time is an essence sometime. It may take some point away from you guys. Well done, well prepared. Actually, this project, it's a go. We're doing it right now, preparing a budget for it. And looks like everything that you explore is what the other engineer has already told us. Thank you.
Yes,
Thank you, Ayub.
Yes, sir.
Thank you both.
Thank you so much.
Thank you for everything.
Anyone one question? So from south, let's move to the north. The last but not least team, BJCC Engineering, and the mentor is Michelle Austin and Mike Giardulo. Go ahead, guys.
Running.
All right. Can you hear me?
Yep.
All right. So we are BJCC Engineering, and we designed the roundabout at Taylor Road and Cooper Street in Punta Gorda. Our mentors were Mitchell and Michael. A little bit of background on the intersection. So Cooper Street and Taylor Road are 2 of Punta Gorda's oldest roads almost, and they're good passageways for trading and transportation back in the day during the city's development. Both roads are 2-lane bidirectional collector roadways that lie very close to the interstate. We have I-75 to the east and US 41 to the west. So we have a high school. Okay. We have a high school to the north of the intersection. We have a middle school that's next to the high school. We have a church to the west, and we have an elementary school to the north. So there's a lot of inflow and outflow traffic going through that intersection. Next. A little bit of the scope of work that we were required to do for the project. We were to design a roundabout at the intersection or find alternatives to the roundabout. We are to acquire necessary right-of-way that is in the limits of the roundabout or our alternatives, adjust utilities as necessary, design new drainage around the roundabout or our alternatives. We are also required to make cost estimates for our roundabout and alternatives. Some constraints, concerns, and problems. At the intersection, there is a long queuing time at the peak hours, which is probably when there's church on Sundays or during the week, and when there's schools in the morning. There's a long time of crossing due to the length of the intersection crossing. It is at a weird angle, creating obtuse and acute angles. So the time of crossing is a little bit longer than usual and causes distractions and accidents because of the length. There is a misuse of right-of-way along Cooper Street. You can't see it in this picture, but down a little ways, it is all the way to the left or the west, and there is hardly any room to work with on the left side. It is not pedestrian or bike friendly at that intersection. There's no existing crosswalks that are clear for drivers, and it is in a school zone, so that is very important. The circular roundabout is a concern too because of the right-of-way and the existing boundaries, and the intersection itself, creating those angles is hard to put a complete circle there. So in our design options, you'll see that we created a different idea for a roundabout.
Okay, so I'm Carter. I'm going to be talking about the design options that we considered implementing at the intersection.
So the first design option is actually to implement an oval-shaped roundabout at the intersection to maximize the traffic flow efficiency. And if designed properly, this option would be effective in reducing the traffic congestion as well as the severity of collisions which occur at the intersection. And on the right side is actually our original concept drawing for this design option. So for a second design option, we decided to consider implementing yielding right turns on Taylor Road only, which merge onto Cooper Street. And this design option was based around a traffic flow analysis, which we conducted. And it showed that during peak hours, the majority of turn movements were right turns off of Taylor Road. And then finally, our third design option was to incorporate traffic calming components and improve signage on both roadways as they approach the intersection. And these components are designed to keep drivers alert of pedestrians and other vehicles. And it can effectively reduce driver conflict as well as improve the walkability of the intersection, which in turn increases the pedestrian safety. So if I can get the next slide, please. So this is our updated concept drawing for our oval roundabout design option. And it's worth noting that this design avoids requiring any realignment of the existing roads, which can substantially increase the cost as well as alter the traffic patterns that already exist. The drawing also displays that the signage, which will be used at the intersection to alert drivers of yielding and pedestrian crossers. However, it's also necessary to acquire right-of-way on the northeastern and northwestern sides of the intersection, as well as to relocate existing utilities. This design also accounts for changes to the pedestrian pathways in order to maximize the pedestrian safety at the intersection, because the existing sidewalks will be impeded by the new roundabout right-of-way that has to be acquired. And it's worth noting that this option will significantly reduce the opportunities for traffic collisions to occur at the intersection, which are often referred to as conflict points. Next slide. Okay, so this is the concept drawing for our second design option, which is the yielding right turn lanes off of Taylor Road. Similarly to the roundabout design option, you can see that this will avoid any realignment of the intersection, but it will also require that the right-of-way will need to be acquired in the same exact places on the northeastern and northwestern sides of the intersection. The design also shows that the right turning lanes will be implemented on Taylor Road and will include both a deceleration lane on Taylor Road and an acceleration merging lane on the Cooper Street. These lanes will allow for drivers to better react to oncoming traffic and decrease confusion due to the existing awkward lines of sight. Additionally, adjustments were made to the pedestrian pathways to account for the acquisition of right-of-way, which would impede on existing pathways. With proper design, this option will improve the traffic flow and queuing time for vehicles significantly. Next slide, please. So this is the concept drawing for our final design option, which is the traffic calming components and improved signage. No adjustments to the existing roadway alignment is required, and it's also not necessary to acquire right-of-way, which will significantly reduce the cost of this project. Additionally, the sidewalks will remain unchanged. So the drawing displays that the signage will consist mostly of pedestrian crossing signs in order to raise awareness of the pedestrians and increase the pedestrian safety. Landscaping will also be implemented around the intersection to promote driver awareness as they approach and almost create this sort of discomfort for them so they pay more attention. The benefit in this project is basically it's low cost, but it still has the ability to improve pedestrian safety as well as potentially reduce traffic flow.
Hello, I'm Kurt. And for the preliminary cost estimate for the over roundabout design, it was calculated that the cost of the roadway would be $745,000. The signing and marking would be $24,000. The cost of landscaping would be $45,000, and the total cost for construction inspection was 12% of the total cost, which was $97,000, bringing the subtotal to $900,000. For design option 2, which is the yielding right turn lanes, the estimated cost for the roadway was $240,000. The signing and marking was $12,000. and the landscaping is $10,000, which is a total of $250,000. And for design option 3, which is the traffic calming and improvements, the roadway was estimated to be $43,000. Signing and marking was a subtotal of $7,000, and the landscaping was $9,000. And we decided to do a single lane oval shaped roundabout because it best fits the intersection and it reduces the conflict points from 56 to 16. And this would also reduce the severity of collisions as well as traffic congestion and also improve pedestrian safety. And here you can see the Taylor Road and Cooper Street growth trends. And they show that the annual average daily traffic for these streets are increasing exponentially as the area gets more populated, and these streets are located next to schools and a church. So these roads are highly congested. And here is the level of service calculations. And these were performed using FDOT annual average daily traffic on both roads in both directions. And we used to calculate the directional design hourly volume as seen highlighted in yellow. And these were done by adjusting the annual average daily traffic by the K and D factors for each direction. And you can see the annual average daily traffic for Taylor Road northbound was a level of service D, southbound C, and for Cooper Street northbound, it was a level of service of E, and the same for southbound.
Okay, so I'm Jonathan, and right now we're looking at the drainage system design for the final roundabout that we chose. We're using type 4 inlets throughout the roundabout just to remain consistent, and they met the requirements necessary to provide drainage for the stormwater calculations that were made and the estimated rainfall that the area receives. This is consistent with the connecting roads, and it should allow for smooth transitions visually and allow for simpler construction to help reduce cost a little bit on that front. And here are the road cross sections. They're slightly different for Taylor Street and Cooper Street. This is to account for the higher traffic, as we talked about earlier, those right-hand turns going southbound. Those are accounted for with that different cross-section there. You can also see the use of brick pavers in the median, and that'll help provide visual continuity throughout the roundabout, as well as providing durability so that the maintenance will be lowered in the long term. We're also able to repave over the roads that are existing throughout some of the connecting portions of Taylor Road and Cooper Street. This is going to help reduce the cost further because this option is the most expensive. So we wanted to do everything we could to keep it within a reasonable budget as possible.
Prepare to wrap up.
Okay. And we're looking now at the detailed cost estimate for this option, the final option we chose, the roundabout. This is all of the details for the roadway construction, and the total for that would be $745,000. And then this is for all the other things included. Signing and marking is going to cost $23,000. And then the landscaping cost would be $40,000. And that's including all of the right-of-way and everything that needs to be included, including the maintenance and then moving the water structures and all of that. And that's going to bring the total cost of the project to $906,000, which is under $1 million, which we felt was reasonable for a project of this scope. And to conclude, we chose the oval roundabout design. Even though the price was higher than the others, it better suited the requirements of this project and was able to provide the best results. The other options of yielding right turns and traffic calming have benefits, but the benefits were minimal compared to the massive benefit of the overall oval design, and for that reason, we chose it. Thank you guys, and we're now open to any questions.
Thank you. So if you have any question for our last team here today?
I had a question. Jesse Gill here. What was your design vehicle for the roundabout? And did you run any analysis for that design vehicle?
The design vehicle was the single axle vehicle. I mean, the volumes, the pavement design is based off the truck or the truck design, but we weren't required to do a pavement design, but single axle vehicle for a single lane was our design.
So the single axle vehicle was the turning vehicle for that job? Thank you.
All right, one very quick question. An oval roundabout, I've never driven around one. Is it, have you seen one? Have you guys explored why the oval instead of a round? And then an oval, does it still called roundabout? Or
it is still called a roundabout, yes. And there are several in Florida, actually. There's one in Cape Coral, I believe Santa Barbara Boulevard,
okay.
And there's one in Miami. But those are even more awkward with more awkward intersections. But I figured this would be good due to the long intersection length and the space between.
A job well done. You just taught me something different today.
Thank you.
What other kind of traffic calming devices did you guys look at?
So there are median traffic calming devices that go in the middle of the intersection, but the way this intersection crosses will not be safe at all. There are traffic calming devices such as you can throw in some curbing, you can throw in more signage to get drivers' attentions to stop for pedestrians, things such as those.
Good, thank you.
Thank you, team. Can you stop sharing that? So again, thank you, students, and thank you, the churches, and especially the mentor that spent time for the whole semester to help us out. And we finished today within time and within budget. Actually, I have no budget for it, so it's zero, so good. And of course, I hope you all stay healthy for this unprecedented and abnormal time, and hope you continue to support us next year, and hopefully we see you face to face, not like this anymore. And good luck to students that you have a new journey, new endeavor. So once again, that we adjourn for today, and thank you all the church, mentor, and student.
Dr. Lang, do you want our score? Do you want me to scan the scores and send them, email them to you, or you don't need our scores?
Oh, no, we need you guys call. Actually, one of the ABET accreditation is the final presentation from student, have the audience and the church from the practitioner like you guys. So, even this is virtual, but you guys and everyone that help us out with that is we really appreciate. So yes, we please send your score to me today or tomorrow, so that will assess them in this presentation.
All right, we'll do. Thank you so much.
Thank you, Ayub.
Everyone did a great job.
Good job, guys.
Thank you.
Proud of you all. We appreciate it. And
thank you, Dr. V.
Great
no
job,
problem.
guys.
Thanks for inviting me to come, and thank you for all everyone who have supporting our program. So that's wonderful, and all the team did a wonderful job. Very impressive.
Thank you.
Thank you.
Thank you. Have a good week, right? Today Monday. Yes. Have a good week, everyone. Not weekend yet.
All right. Bye-bye.
Bye bye, guys.
Bye.
Have a good summer.
Bye, everyone. Thank
Hope
you.
to see you guys
Good
back
job.
on the commencement, the real commencement next December or next year. Yeah.
Party it up this summer.
Yes. Bye bye.
Bye.
Bye. Bye, everybody.
See you.
Thank you, guys.